This is Couchbase 104. We're going to be talking about views and indexing, secondary indexes in Couchbase. The purpose of this webinar is to give you a feel for, how indexing works in Couchbase, how it looks architecturally, and especially if you're coming from, relational databases, this might be a little bit different. And so this webinar will help you understand and kind of get a good grasp of what indexes are in Couchbase and how you create them, etc. This is a pretty full session. We will take a break to answer questions about halfway through, so let's get started. The first thing is, you've heard about views. Couchbase has views, but what is a view? So a view is an index, and indexes are ways of getting to data or information faster. I mean, we see indexes everywhere we look. Even like our file system is a sort of index. If you have, sort of categorical file folders, you know how to get to a particular document or spreadsheet or code in your application based on the folder names, and that's a form of index. So there are other, natural indexes we've created. The Dewey Decimal System is another one. The old card catalogs is another one. And these are all systems to get to information faster. And in databases, indexes are specialized structures to access particular data for searching through data. And usually there's one or two fields that you are searching by in order to find the associated data with those fields. And the same is true in relational databases as well as NoSQL databases in Couchbase. You're picking particular fields that you have known information about and that you're going to query against, and then you're going to get back all the associated data with that. So views are indexes in Couchbase, indexing subsystems, and this is kind of an important thing to understand, is that storing data and indexing data typically in almost every database system is actually a separate subsystem. They're separate from one another. And this means that resources are allocated to each sort of side, or each subsystem. So there's like all the storage of data is in one subsystem and all the indexing of data is another subsystem. In relational databases, indexes are optimized based on the data types that you are using for that index. So if you index, email addresses, those are strings, and they're going to create a special structure for strings. In some relational databases, you can actually pick the style of index yourself and kind of get into the nitty-gritty there. And if that index is a binary, or if it's a, an integer or numerical, it's going to create an index specialized for that. So in flexible schema scenarios, in unstructured data or semi-structured data like JSON, MapReduce is kind of a technique to use to create indexes. MapReduce is actually a general technique. It's been around for a long time. It really was kind of introduced as a way to deal with large amounts of data, particularly unstructured or semi-structured data. As the semantic web grew, you had all this data, and being able to look through it and find patterns or find information was difficult. And in order to make it parallel, so if you do a query in a relational database, you're doing a query against tables. And you can't parallelize that. So if you need to process that, you can't actually do that in parallel. Each one has to happen one at a time. It's very difficult to do in parallel. But with MapReduce, this technique, you can actually go through lots of different, you can have lots of different computers looking through the same data, that's partitioned and parallelized. And so Hadoop is an example that uses the MapReduce technique, and lots of systems use the MapReduce technique. In Couchbase, we use MapReduce to create indexes. So what are the parts of a map and a reduce? So a map is basically a function that identifies data within collections and processes them and outputs a transform value. So that's the sort of general understanding of what a map function does. And if the output transform values are numerical, you can also use a reduce to compute aggregates on that numerical information. In Hadoop and certain other systems, MapReduce is still a general technique, so you can actually nest MapReduces together. So, like for instance, you might have a huge amount of genetic information, and you're looking for a particular gene sequence within all that genetic information. You actually might do that in an iterative fashion, with multiple MapReduces. Now that is actually different than Couchbase. We are using the MapReduce technique, but in Couchbase, we are using MapReduce specifically to produce an index structure. So map functions, as you do your CRUD operations and you're creating JSON documents in Couchbase, our map functions will output data and that will be added to or modified within an index structure. In our case, we have a B+ tree on disk. And so when our output from our map functions are specifically tailored to insert, update, and remove from the index structure. So as CRUD operations happen, these documents are created. They go to each of the map functions, they get processed, and in the emit call or the output call, it goes into an index. So here's a sample view. We write them in JavaScript. On the Couchbase backend, we use the V8 engine to process these. So here's this function, and so all your documents are going to be going, into that function. There's two parts, two parameters here. There's the actual JSON document, that's the first parameter, and there's the document metadata also gets passed to the function. And then what we're doing here with this sort of if statement is filtering, basically. If their JSON properties don't match, in this case, we have specific ones we picked. If it doesn't match, then it doesn't pass with the true, so then it gets filtered out. So if the document that's coming in is a brewery document, where the doc.type is brewery, then it's going to be filtered out of this index. If all these parameters match, it's going to go to the emit statement, and the emit statement has two parameters, the index key and the index value, and that's basically the emit statement puts it into the index structure. So, as you're doing your operations with Couchbase, you are going to be passing them into map functions, and these map functions will be putting them into indices. Or indexes, the improper term that most people use. So here's that sample view. So we're creating an index of basically beer names, the doc.name, and the alcohol by volume values, the doc.abv. So we're filtering documents, so only JSON documents that pass the if statement, where the JSON key doc.type is beer, and there's a non-null brewery ID, and the name is non-null. And then it'll output the first parameter is your searchable parameter. We call that the index key, and that's the doc.name. And then we also have an associated numerical value that we're outputting for that, and that's the alcohol beer by volume. So let's look at the architecture of indexing in views. So when you're creating your storage operations, the first place it goes is into the RAM cache. It goes into the disk write queues and replication queues, and we talked about this in Couchbase 101. And then when it gets to the top of the disk write queue, the IO writers will write it to disk, and at that point it'll pass to the indexers. So the indexers, in our case, they're called design documents, and we're going to talk about that a bunch. After it gets to disk, it goes to the indexers. The indexers process those documents in batches and add them to the indexes on disk. So these are two separate structures. So you have your storage of your documents is one structure, and then you have your indexes is another structure. So you have two different structures on disk, and the indexes are optimized for searching, of course. So views, by definition, are eventually consistent. Okay, so we have Couchbase is a consistent database because your data is the JSON documents, but your indexes, your views, will be eventually consistent. So here we're doing storage ops, and they get into the RAM cache, and that, let's just call that time 1. You can immediately read that. So we do have that consistency, so you can read your own writes. But at the same time that you're doing those reading, it went to the disk write queue, it made it to disk, it got to the indexer, and then got indexed, and that would be time 2. So because there's a gap between time 1 and time 2, by definition, it's eventually consistent. So indexes are eventually consistent, while our CRUD operations and Couchbase itself, is actually consistent with your data. So do you understand? So just so you understand the difference between the two, your data is consistent, your indexes are eventually consistent. So why do we use this MapReduce indexes? First of all, it's because your schema is flexible and your data can vary from document to document. It's very much like the semantic web. And so if you want to be able to find documents by different JSON keys, you use a MapReduce index. If you want to query for documents based on many different JSON keys and values, again, you're going to need a secondary index, a MapReduce index. And if you want to create statistics and aggregates, that's the other reason you would use the MapReduce, specifically the reduce. When are indexes necessary, or indices? Documents that are keyed by random properties and don't use a lookup pattern that we talked about in Couchbase 103, you'll need a secondary index to be able to query properties within that document to actually get that document key. If you're iterating through lists of documents and you're not using the counter ID pattern, or if you have random keys, then you're going to create a secondary index of those documents based on some of those document properties. And also, if you want to be able, so let's just say you key your user documents with the email address, but if you want to look up users by zip code, for instance, if you want to actually look up users by a different property within the JSON document that's not within the key, then you're also going to need an index for those, for any of those additional properties. So key patterns work for a lot of things, but they don't work for everything. So they don't, you can't actually search by different properties by including everything in the key, because it's not possible. So because you also need to know all that information to do a get operation on that key. So that's where the MapReduce indexes come into play. So, that text is a little bit big at the top there. So Couchbase buckets are our namespace, and within that namespace, all the keys have to be unique. And then we have what's called design documents. And design documents, they actually are JSON documents, but the design documents have our view definitions, our map functions within them. So design documents are a verb. The way I like to convey the information that helps people understand it is design documents are like verbs. They are indexers, okay? So we allocate resources to an indexer, and that indexer is a single-threaded process, and it will index the view definitions within it. So each view definition has a map and reduce, or just a map function, and the indexer will process all the views defined within it at the same time. So whenever the indexer runs its batch, it'll update all 3 of those views on the left-hand side there, all 3 of those views at the same time. It'll process the documents with all 3 of those map functions and or reduce functions. Of course, the design documents and all the documents that get passed to the indexers are all within the same bucket. So the bucket is sort of the namespace for design documents as well as unique keys. So indexers are, a single-threaded, one core process. At this moment, we're talking about actually having, additional resources on each design document or configurable, and they can only access data in the namespace. And when they're triggered to run their next batch, they're all the views within a design document are updated at the same time. So here's the map function sort of anatomy. Every document, again, passes through the view map functions. This is the JSON doc, the first parameter. This is the doc metadata. And for people coming from relational or not as familiar with B+ trees and things like that, or data structures on disk, Another way of thinking of the emit is that you're all creating a row, a 2-column row. Actually, it's sort of a 3-column row. Um, and the first parameter is what you're going to be able to search by. Okay, so this is sort of what we call the index key. And then the second is the output value that is associated with that node in the tree or associated with that row if we want to use the row paradigm. So here's a single element index key, right? In this case, it's a text-based key. And we have the output of the user's points, and we're doing email and points. Now for every row or every node in the B tree, or every row, we're gonna call it rows for now, just to understand it. We also include the document ID, which is the document key, which is meta.id. So you don't actually have to output the meta.id because it's always included. So then the searchable column is the doc.email, and then the output value is doc.points. So remember I talked about, there are different structures in Couchbase and different subsystems. So when you're storing your documents on disk, that's one data structure, and when you have an index, it's another data structure. So in this second parameter, doc.points, if I just outputted doc, which is the entire JSON document, what happens is that we actually now have sort of a consistent copy of doc, the JSON document, in RAM and on disk. And then we have another copy within the index structure on disk because we're outputting that as a row value. So what we're doing is actually doubling our storage requirements and on disk because we have 2 copies of that document, and also the one in the index structure is only eventually consistent. So that means if you're modifying that document, it'll eventually get into the index and be part of that row. So it's highly recommended that you don't output the entire document as a row value or as a node value because it is eventually consistent, and it could confuse you as well. And it bloats the index. It bloats the index with too many values. However, outputting values here, a few or several values is completely fine. But just don't do the entire document as the output. So this is called a compound key, index key, and in this case, it's actually an array. Now, array-based index keys are still strings with square brackets on the end. They're still sorted as strings. The index structure of the B+ tree is sorting all index keys like strings, but we can do some things with reduces on arrays by splitting on commas, and we'll talk about that a little bit. So this is an array key. I'm taking basically the timestamp, and we actually added the date2array function to convert timestamp values to an array, and we're outputting for that row a 1. So we can do sort of a count. Count in our reduce. We're going to reduce that. So if we want to look at all the values or all the things that, all the documents, or the number of documents that occurred in 2012 of this particular type. We don't have an if statement here. So all the documents that have a timestamp of 2012, we can set the group level and reduce together to say how many documents were timestamped in 2012. We set the group level to 1, and it'll basically split that array on the commas and then group everything on the first parameter, so we'll get all of 2012, or we can set group level to 2 and we'll get all of October 2012, etc. And you basically just can move along the group level. So that's called a compound key, and you can use that for interesting stuff as well. So for querying views, you're querying them over HTTP. So it's port 8092, and you can do it actually outside of the SDK by curling it or putting it in your browser as well. We have a bunch of different query parameters. So the key equals is used for an exact match of an index key. So I'll kind of show you that in a minute. Keys within array notation will match a set. So like where in relational database, where equals for key equals. And then we have range queries where we do a start key and end key. And those are actually start key and end key of the index key, not of the document key. So our indexes are first sorted by the index key. And then if the index keys are the same from one node to the next, it'll be sorted by the document meta ID within that range. So it's like the second level sort will be the doc ID. So you can actually use the combination of start key and end key and start key doc ID and end key doc ID to page through a result set, especially a result set that keeps changing. You can actually page through that way. And then this is an important one, the stale equals false, and we're going to talk about what that means. And then there's the group and group level. Actually, I should say group level, not group by. So that's used for reduces and aggregate to group on those parameters. So the most common queries are pretty much range queries. I mean, when you're using these indexes, you'll find that range queries are quite common for you. So in this case, we're doing a start key and end key using string match from B1 to Z, capital Z, and it's going to pull all these this entire range of values. And then, if we change it to ZN, it won't include, that last result. So you can see it's sort of a string comparison. And we're going to talk about letter order in a minute right after this, so you can understand how these start key and end keys work in terms of letter order as well. So, and then there's like a straight index key match where you key equals, there's an exact match. Then you have the array notation, and where you can get multiple sort of set matches. And then, so this is also an important part. So with any sort of range queries, so there's other queries too, and we're gonna talk about it when I do some of the demo as well. So the letter ordering in our view indexes, so the way we sort our index keys, is not in byte order. And actually, this is very good that we're using what's called collation order, Unicode collation, instead of byte order. So we're used to byte order in programming because when we do string compare, it's almost always by byte order. That means numbers are less than lowercase a to z, which is less than capital a to z, which is less than, also character variants, like with accents, etc. So what's inconvenient about that is that it's hard to include both lowercase and capital letters in the same query. You actually have to merge them together. So in Unicode collation, lowercase a is less than the lowercase a variance of all the variants of lowercase a, which is less than capital A without variance, which is less than capital A with all the possible variants, which is less than the next letter. That means all the lowercase and uppercase a variants are less than B. So this is very useful. So if I do this query here with which is halfway down, where start key equals y, lowercase y to lowercase z, I won't get all the uppercase varieties of that as well. I'll only get lowercase if it were byte order. So I would actually have to do two queries from lowercase y to lowercase z, and then uppercase y to uppercase z, and merge them together myself. But with Unicode collation, I can just go from lowercase y to uppercase. If I want to get all the y's, including starting with y, from lowercase and uppercase, I just go from lowercase y to z, right? So because z is greater than uppercase y. So that's different. Byte order and Unicode collation are a little different from one another, and it's actually really good that we do it this way. So stale is probably one of the most talked about things when you kind of get used to querying views. So like I said, we index in batches. So what that means is, documents get written to disk, and there are basically 3 different triggers that cause the indexers to update, to index the next batch of documents that have gone on disk since the last batch. Okay, those 3 triggers, 2 of them are automatic. One is time-based, and the automatic ones are configurable. Time-based is 5 seconds. So after 5 seconds, the indexer will run. Or there's been 5,000 CRUD operations, and that will also trigger the indexer to run. Or the stale parameter. Now the stale parameter is actually done in a query, so you're passing this parameter, and we have 3 different options here. The first one is the default, and that is update after. And basically what happens is when you do the query, it'll return results based on the current state of the index in terms of like the data that's actually in the index. And then afterwards, it triggers the indexer to run and update all the views defined within it. So it tells the design document / indexer to run and update all the views within it after it's returned the results back based on the current state of the index. And then there's stale equals OK, which is sort of similar to update after, except it doesn't trigger the indexer to run. So basically, it's reducing your resources, especially for things that don't get changed very often. The stale equals OK is one of those for those use cases where you're not where data doesn't change within these indexes very often. Then you can hit stale equals OK. Remember, this is per view that you're passing this parameter, so you can this is your way of being able to control some of the indexer behavior. And then stale equals false means the indexer should run its next batch and then return results back to my query so that in that case, what we have here is a little bit more latency because it's going to run the next batch before it returns your results. So this also means that at the time at which you do this query, it's only the documents that have made it to disk at that point in time will get indexed. So if you do it before, let's just say you've got a document that's in the disk write queue, and then you query with stale equals false, and it hasn't made it to disk, it will not be indexed in that batch. So just to understand the logistics of the stale equals false. It's highly recommended not to do stale equals false on every query. Otherwise, you're basically asking the indexer to run all the time before running results. So it has to process a batch before returning results. Generally, that update after tends to be, the most common, which is why it's the default. I mean, there are cases where you might want to do a stale equals false, and we can kind of work through that and talk about that a little bit. So we have 3 builds are faster than creating your own custom reduces for this same information. They're sort of native within our library. We've implemented these custom reduces. The first one is count, and it just basically counts the number of items in the index or in the range in which you're querying. For instance, sum will sum the value parameters for numeric values only in the output parameter of the emit. And then the stats actually gives a number of different things together. It does the sum, it does the count. It'll also give you the min and max values and the sum of squares for the range that you're querying or for the entire index. So these are our built-in reduces. When you define a reduce, in your query, you can decide whether you want to use the reduce or not. And so all our indexes are incremental. So that means as you are adding data, we're modifying that the index structure, rebalancing the tree, etc., constantly. And so you're not actually recreating the index all the time. You only actually create the index when you define your map function within the design document. So there are custom reduces, and they're a bit tricky at first. It's kind of a skill of its own. It's like kind of complex recursive functions. You have to learn about it. You got to read about it. You got to practice it. The most common problem is that they don't actually, when people create reduces, their own custom reduces, they're not actually reducing, and they may be increasing rather than reducing, expanding rather than reducing, in which case it'll peter out at a certain number of iterations based on memory and file descriptor, quota, etc. But there are some creative uses for custom reduces, and I highly recommend separating it into a separate design document. Remember, each design document is its own process thread, and so if you create another design document to play with, a custom reduce, etc., it won't affect other design documents or indexers if you have problems with it. If you're causing the design document, the indexer to fail, then you won't affect your other indices if you actually separate it out while you're playing. And generally speaking, whenever you're writing a new view, it's a good idea to actually put it in its own design document, at least temporarily, so that you don't affect other indexes, or other views that you've defined, in case you have a logic error that you've done that causes the indexer to have a problem. So in order to not interrupt, it's a good idea to always kind of use a new design document for that, to sandbox that. So we're going to talk about, we do have a beer sample database that we include, and in the SDKs we also have sort of a tutorial on getting started that is associated with this beer sample data set. I'm going to actually talk about an older version. It actually is, we've changed our key structure and stuff, but the purpose, I want to talk about it as an older version just so you can see a certain ideas within it. So here's a sample document. You don't have to read it all because it's a lot of things on the screen hard to read. I kind of highlight a few things here. In the meta information, we've got the the document key, which is meta.id, which is a randomly generated one. We have in the beer document on the right, we have the alcohol by volume, which is a a float, and then we have a brewery ID, and this is for this beer, which has a name. That's the ID of the referential ID of the brewery that makes that beer. And here's the sort of map function for basically getting all the brewery average. We're going to try and get the average alcohol levels produced by each brewery. And so the index key in the emit statement is the brewery ID. That's what we're going to be searching and grouping by. But we want to take each beer document that has a brewery ID and basically create rows of brewery IDs. Now you're going to have multiple rows with the same brewery ID here, but then for each row you're going to actually have each beer's alcohol by volume that brewery produces. So the emit is creating a row, and then this is the index key, and this is the row value. So this is kind of, when querying that result set, this is kind of what it looks like. As you can see, there are a number of repeated brewery IDs there. So there's a number of beers that they produce. On the right-hand side is the output value, so that's the alcohol by volume for each of those beers. And then you notice in the blue, you see like an ID there, and that's actually the beer IDs for each of those rows. So that's the meta.id, or the document key for each of those rows. Aha. And so we're also going to add a reduce, and we're going to take stats on this, which is the sum, count, min, max, and sum of squares. And we save that, and when we query it, we're going to see a whole bunch of stats, and in the you see the map function and the reduce there, and then down below you see the results, and then the filter results is where you can specify and we're going to go through the interface to specify all the query parameters. So in this case, we're going to be setting the group equals to true. So we want to group all these together. So based on the index key, it's going to group them together if the index key matches from row to row. And then we're also going to reduce that, so calculate the stats on that. So here's just a bigger view of the same information. So for each of these rows here, which is going to be very similar to a JSON result set when you query, we're getting a sum of all the alcohol by volumes. We're getting the count after grouping, and then we're getting the min and max of the output values and the sum of squares. So now, because we have the count and the sum, we can do sort of an average alcohol produced, or alcohol levels, average alcohol levels for each brewery, based on all the different beers that they produce. All right, so let's actually take a little bit of time for some questions, and then I can do some interface, go through the interface and kind of talk through it.
Thank you, Jasdeep. We have a question from Rupesh. What happens if there are multiple emits in a single map function with different keys getting emitted?
Yeah, actually, that's not a problem, and I have a demo of that I'm going to show you. Basically, when you have multiple emit statements within your map function, you're adding all that to the same index. So you're creating a single structure. Each map function, or each view, which includes a map and reduce, an optional reduce, is creating a single index structure. So when you have multiple emit statements, you are combining that information together into a single index. So there are some uses for that, and I'll show you that in the interface. I'll show you one of those.
And then we have a question from Isabel regarding the Unicode collation that you showed a few slides before. Are there options to change the default order of collation?
Not without building it yourself. I think you could probably, it would be very difficult, but you could actually build it from source and try and change that. But no, this has been, the Unicode collation has been there for a very long time, because it's byte order is actually very complex for querying, and the Unicode collation makes things considerably easier. Once you get used to it, you'll understand why.
Thank you, Jasdeep. Let's take one more question before we continue. From Chad, are wildcards supported in view queries?
No, not necessarily. Now you can do, in range queries, you can be creative by doing sort of just the beginning of the string, and range to, I'll actually have to kind of show you. You can do ranges where you kind of have, but it's not really a wildcard. So the answer is really no, because you're basically doing, string searches, and you can't do partial wildcards in it. When you actually have much more complicated queries, so, we've got key patterns, and now we have these views that we're talking about now, and on Monday we're going to talk about Elasticsearch and XDCR in Couchbase 105. But the next level of flexibility in search is Elasticsearch integration. And we also have a query language called Nickel, and actually I'll just show that real quick on the website. So on the left-hand side, you see this N1QL. It's pronounced nickel, it's a pun, non-first normal query language. It is basically a ad hoc querying engine for Couchbase. It's in developer preview 2 that kind of runs separate from Couchbase itself. So this is going to be a third option as well. So there's, our indexes, our MapReduce indexes, our views. Then there's Elasticsearch integration and also ad hoc querying with Nickel. So you're going to have multiple different options here for, kind of querying data. But at this moment, in terms of what's in Couchbase Server right now, without the Elasticsearch integration, is just this views, and no, there are no wildcards in there. Just the kind of queries that I kind of talked about here.
Thank you, Jasdeep. And I want to remind everyone that we go to webinar record every question that you ask. So at the end of the session, we do take out all the questions, and then Jasdeep writes a blog responding to all the questions. So those that we don't take live, you're going to have an answer as well. So
yeah, please feel free to ask as many questions as you want, because I'll answer them in detail on my blog.
Yeah, there are certain questions that are too long to ask live, but we do answer to those as well. So please keep sending questions, and in the meantime, let's resume the presentation.
Okay, design documents themselves are just JSON documents. So here I'm using the beer sample because we all have that data set, and it does come with a few views. And they're actually, when you install the sample data set, you're going to see the design document, and here, so you see _design beer here, is a design document with two views, brewery beers and by location. So those, whenever the indexer gets triggered, the design document is triggered, it'll update both of these views at the same time. So you can copy these over to dev. So let's just talk about what the difference is between these two. Production views are basically live indexes that are going to be triggered automatically for the indexers to run based on the either time or CRUD operations, and they're sandboxed from your sort of development mode, so that you can continue to query them, and they are getting updated automatically, as well as programmatically, through the SDK and the stale parameter. We sandbox the two sort of modes in order to kind of not have any interference between sort of creating new views and things like that, and the ones that are actually being queried and need to be continually updated. So in this case, I can kind of copy them back to the development mode, and I'm going to keep the same name. And there is one there because I had done that earlier, and so it's asking me if I want to update that. And so now I'm in the development mode, and so here are the views here. And when you actually query the views, we have basically what's called the development time subset here. The show results is querying it. Development time subset and full cluster data set. So the difference between those two is, especially if you have a large, a very large collection of documents, you don't want to actually run your queries against the entire data set, or even generate, when you do the show results, you're actually generating an index on disk as well. You don't want to actually do that with the full cluster data set when you have a huge data set, because it does take time to index a large data set, especially if you have like 1 million+ documents. You don't actually, while creating your view, want to do that. So we have what's called the development time subset, which sort of takes a sample across your partitions of Couchbase and indexes those. Then you can actually still, once you're pretty satisfied with with the results you're getting, that this is working for you, you can run it against the full cluster data set. Now that takes time to index. If it's a large collection of documents, or a very large collection of documents, it is pretty fast. But again, if you have 1 million+ documents, doing the full cluster data set means you're actually creating that index. Now there is some sort of use for this, because we actually do like an MD5 hash of this map function, and if you do create this index on the full cluster data set on disk by doing the full cluster and querying it, when you publish, so let's go back here, when you publish from your development time to production, it'll recognize that that index has been created, because the MD5 hash of the map function will and map and reduce function will be the same. So it will use the index you created in development mode, that is the full cluster index. It won't do it again. So that's actually can be useful as well, to kind of, before you get it into production mode, to like generate it that separately in the development mode. Of course, if you change it again, change the map function definition, you're going to have to create a new, you're going to end up creating a new index structure again. So, so let's look at this one actually. This is the brewery beers, and the question was asked: can you actually have multiple emit statements in a single map function? And the answer is yes, you can. So, in this case, what we're doing, so we have brewery documents and we have beer documents. So in the brewery documents, we are we have a brewery name. So let me actually just do go ahead and query this so you can see. In the actual data sample that's included with Couchbase, we changed our IDs to actually be the brewery name and also the beer name as the key, instead of randomly generated in the example I showed before. So in this case, what we're doing is we're creating a single index structure. If it's a brewery document, the doc.type, we're going to emit the document key, which is the brewery's name, as a single element of an array. But if it's a beer document, we're going to emit an array. We're going to emit the brewery ID, so the brewery name, comma, the beer name. So what happens in terms of string sort is because we have this array with, for breweries, it's just one element in the array, and then for all the beers that they produce, it's a two-element array. So this is actually a beer name as the second parameter. And the brewery documents get sorted first. So we've kind of taken two different sets of documents and joined them together. So this is kind of what's called a simulated join, where we've joined two different types of documents together. Now they're grouped together. So here, because I always forget the names of these, here what I have is the same results. This is the same sort of view, but in production mode that has the full data set. And in this case, I actually have a start key of the name of the brewery and an end key of the name of the brewery, comma, and the capital letter Z. So basically all numbers and letters up to the capital letter Z and including Z. So what happens in this case is now I've got a list of, I have the brewery and all the beers that they produce in this index. So when I can basically say, I can get the brewery, it depends on my web view, I can actually just list the brewery and all their beers in a web view by querying this. This is kind of an interesting way of joining. So let's actually modify this real quick. Let's go back to this, and this tab's on development view. I actually want to edit this, and I want to have an output value for each beer. So doc.abv. So abv. Save that. So I'm going to click it once, and it's already updated the index. And I'm going to go ahead and do this on the full cluster data set. Notice I had to click it multiple times because the default was update after. So I clicked it the first time, and then I triggered the index to run. It's creating an index structure on disk, and then I clicked it again, and it showed results in the query. So there is no value here for the brewery itself, but for each of these beers, it has that alcohol by volume. So I'm going to actually do a stats reduce on this, and I'll do it on the whole clustered data set. Hey. Oh, that's right. So I actually, oops. I need to change this so that reduce is true. Oh, I'm on the wrong tab, but I do want this actually. I want this value. I'm going to do a range here. Oh, I have an error. So I don't want a null value here. I need a 0 value here. There we go. So this is actually the average of all the beers together. So what I want to do now is go from 512 to 512, but in this case, I only want this brewery and its beers. So I'm going to start with 1. Oops. And then go to Z. So see, I'm doing a range query here. Oops. Where I'm getting this alcohol by volume for this range. Oh, sorry. Is there any other questions while I'm actually figuring out what I did wrong here? From brewing company to brewing company.
Yeah, we have we have a few other questions. One is it's gonna require you to do some more demo. So another question is if you could model a graph with views.
Graphs are quite difficult. So no. I mean, you can't really model a graph with oh, I'm not even on the full cluster data set. You can't model a graph with relational or really NoSQL. I mean, when you're talking about a proper graph. Now, it just really depends. That is kind of a long question. And it really depends. And so what it depends on are a few things. And the few things are um, how you want to query the graph. Okay, so if you want to query the graph based on the relationships between nodes of your graph. So if it's based on the sort of qualities or attributes of the relationship, that's actually very complicated. And also the number of levels in which you want to traverse the graph is also complicated because it grows exponentially in terms of the number of operations you need to do. Um, Pretty much for any non-graph database that is not organized as a graph database with doubly linked lists and easy traversal across nodes, um, with fixed, basically they do fixed size doubly linked lists to be able to optimize traversals and relationship queries. So things like Neo4j, etc., are optimized for those particular kinds of queries, but they're not very good as general purpose stores. So they're optimized for graph queries, but not general purpose. And so actually using a combination, and I've done this many times actually, where I used a combination of Couchbase and Neo4j together, and it's great. I use Couchbase for all my session and general purpose store, all the user data, etc. And then I actually create a graph, and I only include the information that is required for traversal in Neo4j, and I kind of combine them together so I can do graph queries and then take the results and pull it out Couchbase for like particular nodes if I need full information. So that's how you would do it, I think, in my opinion, because graph traversals and queries. Now, if you have a simple quote graph structure where you only have like Twitter. Twitter only has followers and followees, right? People you follow and people who follow you. That's not a complete graph. So you're not traversing, multiple levels of relationship there. So that's actually quite simple. It's not actually like a graph. But then you have LinkedIn when you actually, on the right-hand side, will see like how many uh, degrees of separation you have between yourself and another person. That's actually a real graph traversal. In which case, both relational and the majority of NoSQLs besides like graph databases will be able to do that efficiently and fast. So.
Okay, and
Sorry, that's a long one.
Yeah, it's gonna be probably answered better on the blog as well. We have another question from Matteo. If you can show us again a simple reduce function code, which it might help understanding better how it works.
Okay, so all right, so I'm gonna actually I'm gonna just go ahead and create a new design document called, that's not a great name, myDD. I'm gonna create a view. Since I'm using this data set, there's not a lot of reduces I can do, but I'm gonna do by ABV. And it is similar to the demo I gave before, but just to be able, because there's not a lot of things that I can actually, in this data set, I can reduce. So let's see, I wonder if I can type and zoom in at the same time. Yeah, so you guys can see a little bit better here. If doc.type here,
If you can read what you type, because it's really small on the screen.
Oh, you don't see the zoom?
No.
Oh, I thought my screen zoom went to GoToMeeting. I guess it does not.
I'll go
Okay.
to webinar, doesn't
Yeah.
accept that.
Okay. All right. Let's see if I can increase the. Okay.
Yeah, that's better.
Sorry, I thought I did a screen zoom and I thought it translated over. So here I'm looking at all the beer documents. This is the example I was giving with the slides, but I'm going to emit the doc.brewery ID, and then the output value would be alcohol by volume. All right. Let me make this a little wider. Save. Oh, let's put the stats. Save. Oh, I have a, oops, colon there. Save. All right. All right, so this, basically reduced, this is all the beers and within the development time subset. Just building it. And this is all the beers in the full data set. This is a reduced, so I have the count, the sum, the min, max. But this is not as useful for me. So what I want to do is actually group them by the brewery IDs. So in this case, I'm grouping them by each brewery, because when the emit statement I have the doc.brewery ID. Now there's multiple beer documents that will have the same brewery ID. So if I do, let me show you what that looks like. Oops, I didn't mean to click that. So if I take reduce equals false here and ungroup and do the full cluster data set, I'm going to see that I have all the same index key over and over here, because each of these beers have the same brewery ID. Okay, so now I'm going to reduce that, but I also want to group it by that index key. So in what case, now I have all the stats by brewery ID here, right? So I'm doing the stats on it, and this includes the count. I mean, if I just did, count just by itself, then it'll just have counts on them. Oh, it's building it. Right, so that means that's how many, it's also how many beers they have. I'm sorry, that's the total alcohol by volume. I'm sorry, that's the count. I did count. So this is the total number of beers that they have, that each brewery has. So I generally use the stats because it has everything. Oops. So, I mean, I hope that's helpful. So any numerical information that's in the output here, you can kind of do a reduce on, and then you can group or group level. I can also, this is going to be kind of random. It's not exactly reduced, but I'm going to show you, let me show you, I'm going to do a count here. And I'm going to show you the group level query. So I'm going to do a date to array. Let's make sure it has an updated timestamp. Date to array dot updated. As you can see above, there's like a updated timestamp. And I don't need the alcohol by volume, so I'm just going to put a 1 there and do a count. So now I can see when these documents have been updated, and I can group it. This came off some public data set. So in this case, I'm going to do the group level of 1 and reduce with the group level 1, and that's how many in the development time. This is how many beers were updated by year, because I set the group level to 1, which is the first element of the array of the index key, which is year. And then let's set it to 2, and I can do it by month, year and month. Let's keep it on the full cluster data set. So now this is year and month. This is the count of the number of beers that were updated during this month. And month and year combination. And then, of course, I can increase the group level and keep on going. All right.
Perfect. I think that's all the time we have for today, since it's already 3 minutes past 11.
Okay.
But if you have any other questions, please email us at webinar@couchbase.com or just deep@couchbase.com, and we will respond to you as soon as possible. Also, just Deep will answer to all those questions that we haven't answered during this session. And finally, last reminder is on next Monday, we will have our first Couchbase 105, and it will be focused on cross-data center replication and Elasticsearch. As you know, we have a plugin for Elasticsearch, and we will describe it in details during this webinar. I posted the link to register on the chat. With this, I want to thank Justdeep for this session and everyone for attending, and I hope to see you on Monday.
Thanks for coming.